My name is Yu Wei from AUS Chemistry Department, and now is a year 3 PhD student. Today I'm going to present our recent work on the two-dimensional ferromagnetic material and the application of scanning probe microscopy in such ferromagnetic materials. As we know, the graphene is the typical 2D materials, and it can be peeled off from the bulk graphite. And here is the structure of the graphene and graphite crystal structures. And there also has many kinds of 2D materials like the MOS2 and black phosphorus, and also there are many transition metal dichrogenic. And in the 2D materials families, there has many different physical properties, ranging from the insulator and later to superconductors, and also the cross insulators and others, such as ferromagnetism and ferroelectricity. And also the 2D material is promising in the next generation ultrathin and flexible devices. So this research area is still very hot. Okay, and scanning probe microscopy in 2D materials. As we know, the AFM is a versatile techniques in material science, also in the 2D materials. Here is a very simple working principle of the AFM. I think all you are here is expertise in AFM, so I will not explain here. And the red fold image is the typical modes used for the 2D materials. We want to see the thickness to know how many layers of the flake. So the topography and the height is very important for 2D materials. And also the work function mappings from the current probe microscopy, and also the current mapping using the conductive AFM. And the last one is the ferroelectric switching using the piezo response force microscopy. Now it's widely used for the ferroelectric materials in 2D materials. And I'm going to talk about the 2D ferromagnetism. The 2D ferromagnetic materials has just been found 2 years ago in 2017. The two research groups from the Professor Xu Xiaodong and Professor Zhang Xiang, found these two kinds of ferromagnetic materials, CRGT and CRI3. And from 2017, these 2 years, there are many kinds of, there are many Nature and Science papers regarding these two materials. And also, they also have some new materials coming through. Here we are focusing on the ferromagnetic vanadium diphenylide. VSE2 is a typical 1T phase transition metal dichrogenic. You can see from this crystal lattice. It is a 2D material, has 1T phase. And the first publication on its ferromagnetism is just last year. They also grows the monolayer VSE2 film in the high vacuum system using the molecular beam epitaxy method. And they use the squid to confirm its ferromagnetism. Squid also is a widely used method to see the magnetic properties. However, the ferromagnetism for VSE2 monolayer is still under debate because there are some following groups they repeat the growing of the monolayer VSE2, but they found from their past study they didn't see any magnetic exchange density. And also this year, there's another work. They found, they proposed the reasons for such result because they think the ambiguous sample because they are from the tiny domains and the domain is misoriented and there are many grain boundaries. Such effect will induce the spin frustration. So they suggest the VSC2 monolayer is a spin frustrated magnetic. So it is necessary to introduce another method to prepare the monolayer VSC2, especially from the top-down exfoliation method. So here we use a very simple preparation method using electrochemical exfoliation, using such big size organic molecules to intercalate inside the interlayer gap and expand the flakes. Then we can see from this image many different sizes of flakes can be found. And the biggest size we can find is more than 120 microns, so it's quite big. And we did a statistic investigation, then we can find the thickness below 5 layers is more than 19%, and the average size is around 40 microns. And also we use the AFM to see the topography and the thickness. You can see from the first image, the top layer, top 40 layer has the thickness of 1 nanometer. So it can prove that the flake is monolayer. And also we did other characterizations to check, such as the EDS and atomic result, the TM and Raman, to check its high quality. And we found that the VSC2 monolayer is extremely air sensitive. When we expose to the air, it will degrade within a few minutes. So we need to find some rules to passivate the VSC2. Then it can be used for. It can be worked in other ferromagnetic techniques such as the NFM, because NFM is used it's worked in the air, so we need to have using the stable materials. So here we introduce a simple chemical passivation method using such molecule with the psi function group. Because in 2D materials, the instability of the materials always because usually is because the sulfide or selenium vacancies. So here we use the psi function group, which can bind with the vanadium in the vacancy site. So it can passivate the vacancy site. Here is the simple passivation route, and we also use XPS to see that the molecule absorption is chemical absorption, not physical absorption. And here we use the XPS and AFM topography to monitor the passivation effect. You can see from the AFM, without the passivation, the monolayer degrade within 30 minutes, and the bilayer also degrade within 1 hour. But after passivation, the monolayer can survive within 5 hours, and the bilayer can survive more than 1 day. So this molecular passivation is quite enhance the stability of our flake. And okay, let's move to the ferromagnetic study. Firstly, we use the squeeze. It's a common method to see the exfoliated sample. You can see from the first image, there is a obvious ferromagnetic hysteresis loop, which can direct through the magnetic property of the sample. Then we also identify the Curie temperature of the VSE2 is up to 470 K. And also we using the SPM and the XMCD method to study the magnetic property before the chemical passivation and after chemical passivation. We can see the magnetization of the center is greatly enhanced after the chemical passivation. So such chemical passivation makes it possible for our following MAFM study. So I will talk about the MAFM. Here is the simple working principle for the MAFM. The MAFM is a lift mode in the AFM techniques. When the first scan, the tip will close to the center surface. Then now the first scan will collect the topographic information, and then the tip will lift up. Then now the magnetic force will become the dominating force. So in the second scan, it will connect the magnetic signal. So this method has widely used in the inorganic thin-film materials to check just like the image, to check the magnetic grand boundary and the magnetic domains and the domain words. So here we use, since our passivating flake is stable enough, so we can use MAFM to study its magnetic properties. You can see we choose a flake with monolayer, bilayer, and trilayer. Then here is the MAFM face image. You can see the color is quite different. Then the compared to the substrate, the monolayer shows much higher phase shift between than the bilayer and the trilayer. We also can see from the phase profile, the monolayer shows higher phase shift. So it means the monolayer has higher ferromagnetic property than the bilayer and trilayer. So the MAFM result is quite important for our work because it gives direct proofs for the ferromagnetic of these VSE2 samples, and also it distinguishes the ferromagnetic signals for different thickness. Yes, and here is our group, and the professor is Dr. Camping from the AUS Department of Chemistry, and we also need to thank the collaborators from MAC department and the physics department. Okay, thank you.